In a sample of pure water, all the water doesn't remain as molecular H2O. A small amount of ions will actually be formed. This is called the autoionization of water, and it occurs when water reacts with itself. We've seen before that water has the ability to either function as an acid or a base. It contains 2 protons, so it could be a proton donor and act as an acid, but it also contains 2 lone pairs of electrons, so it could also function as a base. Species that can be acids or bases are said to be amphoteric. It depends upon who they're reacting with if they'll function as an acid or a base. If we have a sample of water, which is all H2O, one molecule of the water can function as an acid, and another molecule can function as the base. An acid is a proton donor, and a base is a proton acceptor. So one molecule will grab a proton from another, acting as the base, and those lone pair of electrons in that covalent bond will stay with the oxygen. This will be in equilibrium with the ions that are formed. When the base picks up a proton, it forms the hydronium ion, H3O+, and when it functions as an acid and it loses a proton, what we're left with is OH-, hydroxide ion. At equilibrium, there's an equal amount of hydronium and hydroxide ions in any sample of water. It's a very, very small amount, and the equilibrium lies far to the left, meaning it's favored on the side of the molecular water molecules, not the hydronium and hydroxide ions, but there still is a very small amount of those ions present. We can write the formula for the autoionization of water as H2O plus H2O in equilibrium with H3O+ and OH-. The hydronium ion and the hydroxide ion is aqueous because it's still surrounded by water molecules. If we were to write our equilibrium expression for this equation, it would reduce down to our products over our reactants, which our products are hydronium concentration times hydroxide concentration, but our reactants are both pure liquids. And we don't include pure liquids or pure solids in our equilibrium expression. So essentially, our denominator is just over 1. Instead of saying it's equal to Kc or Kp, we now call it K sub W, where K sub W is called the ion product constant for water. It's referred to as the ion product constant because we have hydronium times hydroxide, which are both ions, and we're multiplying them together, so we have a product in this case. The equilibrium for the autoionization of water will lie far to the left-hand side, and there will only be a small amount of ions present at equilibrium. The concentration of hydronium and hydroxide present will vary depending upon the temperature. Typically, we assume that we are at a standard room temperature of 25 degrees Celsius. Experimentally measured values of hydronium and hydroxide at that temperature are 1 × 10⁻⁷ molar. If we were to take those concentrations and substitute them into our Kw expression, Kw equals concentration of hydronium times hydroxide, we would see that Kw is a constant at 25 C of 1 × 10⁻⁴. The value for Kw would change at different temperatures, but often we're just assuming that we're at 25 degrees Celsius if we're not told otherwise. This equation is the first one we'll use that will be able to relate hydroxide ion concentration to hydronium ion concentration using the Kw. Hydrogen ion concentration is typically expressed using a logarithmic scale rather than molarity. This is known as the pH, or the power of hydrogen of a solution. The pH is defined as the negative log of the hydronium ion concentration, but for short it's often written as the negative log of the hydrogen ion concentration. Recall that H3O+, hydronium, and H+, a proton, are used interchangeably. Since pH is defined using a logarithmic scale and it's a negative log, as the pH increases, that means that the hydrogen ion concentration decreases. As the pH decreases, the hydrogen ion concentration increases. We can also undo our function for pH and solve for an unknown hydrogen ion concentration by taking 10 to the negative pH. The pH scale ranges from 1 to 14. We can use the pH scale to determine the acidity or basicity of a solution. Solutions that have a pH of less than 7 are defined as being acidic. Examples are our stomach juices, which have a very low pH that allow us to break down food, and things like fruit juices. If a solution has a pH of exactly equal to 7, then it's said to be neutral. This would be an example of pure water. If a solution has a pH greater than 7, it's said to be basic. Human blood is slightly basic at a pH of 7.4, but many things like soap and household cleaners are extremely basic and have a very high pH. Given the following hydrogen ion concentrations, determine the pH. So pH is equal to the negative log of the hydrogen ion concentration. So to calculate the pH, if we're given the hydronium or hydrogen ion concentration, we simply have to plug it in. In this case, we would take negative log of 1 times 10 to the negative 2. When we have a hydrogen ion concentration where the number out front is 1, the exponent will actually tell us what the pH is. If you calculate this using your calculator, you'll get a pH of 2. For our next one, we have 1 times 10 to the negative 7th for our hydrogen ion concentration. So to calculate the pH, we'd have the negative log of 1 times 10 to the negative 7th. And that negative 7 tells us what our pH is. That would give us a pH of 7.0. And the last one, we have a hydrogen ion concentration of 1 times 10 to the negative 9th. So the pH would be the negative log of 1 times 10 to the negative 9th. And our pH would come from that exponent right there. So our pH would be exactly 9.0. Our first one has a pH that's less than 7. So the pH of 2, this is an acidic solution. When we have a pH of exactly equal to 7, this is neutral. And in our last one, the pH was greater than 7, so this would be a basic solution. What is the hydronium ion concentration in a solution of pH equal to 5.76? So to calculate the H3O plus solution, we want to undo our negative log function. So that'll be 10 raised to the negative pH. So we're going to have 10 raised to the negative 5.76 because that was our pH we were given. And our hydronium ion concentration is 1.74 times 10 to the negative 6 molar. Since it's a concentration, it'll be in units of molarity. We can also define a pOH scale, which talks about the power of hydroxide. Anytime we take the P of something, we take the negative log of it. So the pOH would be the negative log of the hydroxide ion concentration. And if we want to undo that formula, just like we did with the hydrogen ion concentration, to calculate the hydroxide ion concentration, we take 10 raised to the negative pOH. We can use these formulas in relationship with our Kw formula that we talked about earlier. At 25 degrees Celsius, Kw was 1 times 10 to the negative 14th, and that was equal to the hydronium ion concentration times the hydroxide ion concentration. If we take the negative log of everything in our Kw formula, we'll get the pKw is equal to the pH plus the pOH. And the negative log of 1 times 10 to the negative 14th is just 14. So we can always use this relationship that pH plus pOH will equal 14. Using this formula, the Kw formula, and our POH and pH formulas, we can solve for missing hydrogen ion concentrations, hydroxide ion concentrations, or pH or POH. We have 6 formulas that we just learned in total, and there's more than one way to go about solving these problems. I suggest doing the way that works best for you, but just making sure that you can get to the correct answer. So here we have an example. Calculate the pH of a ammonia solution, NH3, that has a hydroxide ion concentration of 1.9 times 10 to the negative third molar. Is the solution acidic, basic, or neutral? So since we were given the hydroxide ion concentration, I would start by calculating the POH of the solution. So the POH will equal the negative log of the hydroxide ion concentration. So that'll be negative log of 1.9 times 10 to the negative third molar. Our POH comes out to being 2.72. And then from here we can use the relationship that pH plus POH is equal to 14. We can rearrange and solve for the pH of the solution. So the pH will equal 14 minus the POH, which will be 14 minus 2.72, or a pH of 11.28. Since our pH we calculated is greater than 7, the solution is basic. And we might have guessed that before we did any work because it was the pH of an ammonia solution, which if you remember, ammonia is a weak base. Calculate the hydrogen ion and hydroxide ion concentration in human blood having a pH of 7.40. We were given the pH, so we can undo the pH to get at the hydrogen ion concentration. The hydrogen ion concentration will be equal to 10 raised to the negative pH. So that'll be 10 raised to the negative 7.4, which gives us a hydrogen ion concentration of 3.98 times 10 to the negative 8th molarity. And then we also learned that Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. And we could rearrange and solve for the hydroxide ion concentration since Kw is a constant. So hydroxide ion concentration will be equal to Kw divided by the hydrogen ion concentration. Kw is 1 times 10 to the negative 14th. And we just solved for the hydrogen ion concentration. And we got 3.98 times 10 to the minus 8th. That'll give us a hydroxide ion concentration of 2.51 times 10 to the negative 7th molar. The water in a lake was found to have a hydrogen ion concentration of 3.2 times 10 to the negative 5th molar. Calculate the pH and the POH of water. Is it acidic, basic, or neutral? We are given the hydrogen ion concentration, so the pH is equal to the negative log of the hydrogen ion concentration. So we'll take negative log of 3.2 times 10 to the negative 5th, which that gives us a pH of 4.5. To find the POH, we can use that pH plus POH is equal to pKw, which is 14. The POH will be equal to 14 minus the pH, so that'll be 14 minus 4.5, which gives us a POH of 9.5. When deciding if it's acidic, basic, or neutral, That is usually defined upon the pH scale, not the pOH scale. So we want to look at our 4.5 for that. Our pH is less than 7, therefore the solution is acidic. There are a few different ways to measure pH in the laboratory, and some are more accurate than others. The first way is using something known as universal pH paper. There's a couple different types of pH paper, but universal pH paper will change colors depending upon the pH. You can use an acid-base indicator, or the most accurate method is a pH meter. Universal pH paper will change a certain color when dipped in a solution, and you can match the color up to the chart that's on the container to identify what the pH of the solution is. We'll talk in depth about acid-base indicators later in this chapter, but for now you might just want to know that an acid-base indicator is a substance that is made up of a weak acid and its conjugate base in solution. It has a mixture of both of them, and usually the weak acid is one color and the conjugate base is another color. They're usually organic compounds that contain something known as a chromophore, which changes color depending upon the pH environment. There are many different acid-base indicators. The most common one we've used is phenolphthalein, which is clear and colorless up until pH of 8.3, and then above that, in basic solution, it turns pink. We will also learn how to use a pH meter later in this class, and a pH meter is the most accurate way to get at the pH of a solution. The device will measure the voltage, which is another way for saying potential difference, of a solution, and it automatically converts it to a pH value, which you can read on the digital screen. Later in this class, we'll talk about electrochemistry, and we'll learn a little bit about how a pH meter actually works. When calculating the pH of strong acid solutions, it's important to remember that strong acids dissociate 100%, so all that's present in solution is H plus and X minus. The strong acids are hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, and sulfuric acid. These are at the top upper left corner of our acid-base ionization chart. The strong acids are the ones that have a Ka that say large, where there's no actual numerical value written for them. In previous problems where we calculated the pH or the pOH, we were given directly the hydrogen ion or the hydroxide ion concentration. This is different because it says calculate the pH of a 0.25 molar HNO3 solution. The first thing we want to be able to identify is that HNO3 is nitric acid. And nitric acid is one of our strong acids. So that means that when nitric acid is placed in solution, it will fully dissociate, so we'll use a single arrow, and break up into the hydrogen ion and the nitrate anion. In this equation, we know that everything is 1 to 1 to 1. So if we know that we have a 0.025 molar solution of nitric acid, that means that we also have present 0.025 molar hydrogen ion and 0.025 molar nitrate anion, because all of the molecular nitric acid dissociates into hydrogen ion and nitrate ion. So the concentrations are 1 to 1 to 1 in this case. What we're interested in is the hydrogen ion concentration if we're going to calculate the pH of this solution. The pH is equal to the negative log of the hydrogen ion concentration. So the negative log of 0.025 molar in this case gives us a pH of 1.60. We should expect a pH that's really low because this solution is going to be very acidic with it being a strong acid solution. What is the pH of a 0.67 molar hydrobromic acid solution? Hydrobromic acid is on our list of strong acids. It's also on the top of our acid ionization chart, which tells us it's strong. So when hydrobromic acid dissociates, it breaks up completely into H plus and Br minus. So if we know the concentration of HBr is 0.67, because our balanced equation is 1 to 1 to 1, we're going to have the exact same concentration for our hydrogen ion and our bromide anion. All of them are going to be 0.67 molar. So to calculate the pH, we're going to take the negative log of the hydrogen ion concentration, which that'll be the negative log of 0.67. And that gives us a pH of 0.17. So this is a very acidic solution. We can also calculate the pH in solutions of strong bases. Strong bases are going to be metal hydroxides. So group 1A metals, such as lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and some group 2A metals, calcium hydroxide, strontium hydroxide, barium hydroxide. Hydroxides such as magnesium hydroxide are missing usually because they're essentially not very soluble. So in water they tend to form a solid precipitate rather than dissolving. Calculate the pH of a 0.090 molar solution of sodium hydroxide. So when we make a solution of sodium hydroxide, the solid sodium hydroxide will dissociate completely into aqueous sodium ions and aqueous hydroxide ions. In this case, we know that the sodium hydroxide solution was made up to be 0.090 molar. In our equation, everything is 1 to 1 to 1. So our concentration of sodium ions is going to be also 0.09 molar, and our concentration of hydroxide ions will also be 0.09 molar. So before we calculate the pH, since we know the hydroxide ion concentration, we can calculate the pOH, which will be the negative log of the hydroxide ion concentration. So that'll be the negative log of 0.090. That gives us a pOH of 1.04. Next, we can use that the pH plus the pOH is equal to the pKw, which is 14. Our pH will be equal to 14 minus the pOH of the solution. So we'll have 14 minus 1.04. That gives us a pH of 12.96. We should expect a value like this because sodium hydroxide is one of the strong bases. So we should expect a very, very high pH. We got a pH that was greater than 7, therefore the solution is basic. Let's try another example. Calculate the pH of a 0.0050 molar solution of calcium hydroxide. Calcium hydroxide is a strong base. First, we want to write the dissociation of the calcium hydroxide. The solid in water will break up into calcium 2 plus ions that are aqueous, and we'll get 2 OH minus. We'll get hydroxide ions, but look at your original formula. It was CaOH2, so we get 2 hydroxide ions, 2 moles of them for every 1 mole of calcium 2 plus ions. We know the initial concentration of the calcium hydroxide was made up to be 0.0050 molar. The calcium ions are going to be the same concentration, 0.0050 molar, because the calcium hydroxide and the calcium ions are 1-to-1. The hydroxide ions, though, are going to be 2 times that amount. We have 0.0050 moles of CaOH2 per liter. And if we were to use our balanced equation, for every 1 mole of calcium hydroxide that dissociates, we form 2 moles of hydroxide anions. So we're going to have to take our concentration and multiply by 2 to get our hydroxide ion concentration. Our moles of calcium hydroxide cancel, and our concentration of OH minus ends up being 0.010 moles per liter for our hydroxide ion. So it's 2 times the amount of our calcium hydroxide that we made up the solution as. We're going to want to use the concentration of the hydroxide ion to solve for the pOH first. The pOH will be equal to the negative log of the hydroxide ion concentration. So we'll have the negative log of 0.010 molar. And that gives us a pOH equal to 2. And then our pH plus our pOH will be equal to 14. The pH of our calcium hydroxide solution will be 14 minus the pOH. So we'll have 14 minus 2, which gives us a pH of 12. Once again, our pH is greater than 7, which we expect because we had a strong base. So a pH greater than 7 is a basic solution.